Good morning, everyone. Thanks for joining us on day 3 of I/O to talk about Thread and Google Cloud. My name is Calum Barnes. I'm a product manager on Google Cloud IoT Core.
And I'm Jonathan Hui, Principal Software Engineer at Google Nest and VP of Technology for the Thread Group.
So we're super excited about this session today and to tell you a little bit about things that are happening in Thread and IoT Core. Before we get started, can we just see, maybe show of hands, how many of you here have heard about Thread before? OK, most of them.
Yeah.
That's pretty good, Jonathan. And what about IoT Core or used Google Cloud in any way before? Also pretty good.
Nice.
OK. So if you haven't heard about them, don't worry. We're going to give a little brief intro when we get started here. If you have, I think we have a really, really exciting session today because we are going to be demoing for the first time MQTT and TCP over a Thread network all the way up to the cloud. And we're also going to be showing COAP communication to IoT Core. But before we get started, I want to talk a little bit about what our requirements for the device that we're going to build and demo today are, and how they differ from maybe some of the current IoT devices, whether they be smart home or commercial buildings that are on the market. So for the devices we're going to build today, we want them to be very, very low power. So this means not just having long battery life, but also being able to work on very, very small batteries for long amounts of time. Next, we want no proprietary hubs or gateways. We don't want to have proprietary application layers or require users to install new hardware for every single device that they buy. And finally, we want IP all the way to the edge. So we want our devices to work with the existing internet standards and protocols that we know are secure and are comfortable working with. But before we get into how we're going to do that, I want to talk about the state of wireless products today. And I think this is true whether you're talking about smart home, smart buildings, industrial wireless products. I think it really runs the gamut. So today we have a lot of devices that are using Wi-Fi, using 802.11. And this works great for many classes of devices. If you have a camera, a smartphone, or laptop, something where you can recharge the battery, you need to use a lot of bandwidth, Wi-Fi is great. But for devices that need to be very low power, Wi-Fi isn't as good. You need to either be able to recharge the device frequently, like your laptop or phone, or you need to do a lot of tricks to end up making it be very low power over time. The other issue with Wi-Fi is when you start having lots of nodes, so especially for your average consumer's home wireless setup, if you want to connect every single light bulb or light switch in your house, you're going to have an issue doing that with your traditional router and still have the rest of your devices work. So we know that even though there's a lot of good Wi-Fi infrastructure in place, it's probably not the technology we want to use to build our next generation wireless and IoT products. So I know what a lot of you might be thinking. Well, there are good solutions out there for this today. We have Bluetooth, we have Zigbee, we have Z-Wave, a number of wireless technologies that will help us build lower bandwidth but lower power consumption, and also scale to large numbers of nodes in small spaces. However, while these do address a number of the issues that we're looking for, they have one critical fallback, and that's that they need lots of these IoT gateways. So since they depend on their own radio technologies, usually proprietary application layers, and tightly linked application backends, you can end up in situations where if you have multiple products from multiple vendors, or even in some cases multiple products from the same vendor, where you end up with a whole host of these devices connected to your router at home, or it can be even worse in industrial or commercial IoT settings. And while this does work from a technical perspective, I think it hurts user adoption in a couple ways. One is it drives up costs. If you need to sell a gateway with the first light bulb that your customer buys, or the first whatever your product may be, you're probably more than doubling the cost for that very first entry point. Next is it creates confusing user setup experiences. Nobody wants to have a lot of these or go through having to learn the differences between setting up a Wi-Fi device versus a Bluetooth device versus a Zigbee device. And finally, and I think what the largest problem is it encourages silos. So the manufacturers of these gateways want every product to work with their ecosystem. And so we end up with silos of functionality as opposed to real network interoperability like we want to build. So I think these are some real problems, but luckily, we're pretty close to having a solution to help with it.
So we were facing these exact problems that Calum was talking about at Nest, where we wanted to build products for the connected home, where we were keeping users not only comfortable, but also safe and secure. We wanted to build solutions where our devices could communicate securely with each other, to cloud services, and to users via their mobile devices. And we also wanted to have those devices to be very low power, because we wanted those devices to last for years on very small batteries. But as we evaluated existing communication technologies, we could not find a single technology that satisfied our requirements. So in 2014, Nest, along with a number of other companies, founded the Thread Group. The Thread Group is a nonprofit organization with more than 100 member companies from around the world. And the Thread Group is responsible for defining and maintaining the Thread protocol specification. It serves as a market education group for promoting the use of Thread in connected products. And it ensures a great user experience through a rigorous and meaningful product certification program. So in summary, the Thread protocol is an open, IP-based, low-power, secure mesh networking technology for connecting IoT devices. It supports the same IP technology that drives every internet-connected device, but is designed to support very low-power applications, including devices that operate on coin cell batteries. Now, for the radio, Thread uses IEEE 802.15.4. It's the same radio that's been used in Zigbee for 15 years. Using an existing widely deployed radio allows Thread products to achieve fast time to market, as well as leverage existing economies of scale to achieve low-cost solutions. Now, at the network layer, Thread uses existing IETF standards for supporting the Internet Protocol version 6, or IPv6, over 802.15.4 radios, a technology called 6LoWPAN. Now, Thread support for the Internet Protocol is a key differentiator, and most existing technologies do not support IP. So why is IP so powerful? Well, first, it means that we can build solutions that utilize a number of link technologies, including Wi-Fi, cellular, and Thread, and have all of those devices communicating with a common single application layer end-to-end without needing to build and maintain application protocol gateways. And at the same time, it means we can have a single network that can support multiple applications simultaneously. IP makes it easy to deploy new applications, and it was a key reason for the success of the internet. And Thread extends that benefit to low-power devices. And specifically for this session, it means that we can build battery-powered devices that communicate securely end-to-end with Google Cloud IoT Core without any application layer in between.
OK, so now we've seen how we are going to use Thread as the radio technology to build these products. And we also know that Thread is going to give us an underlying IP layer link, which means we can use just about any cloud backend that we want to connect these products and leverage data from them or interact with them. But let's talk about first what we need to think about when we choose a cloud product or choose a cloud to use. There are a lot of options out there, and I think a lot of them will probably satisfy what we're going to do today. But there are two big things that you want to think about. First is security, and the second is scale. So security is always important in IoT. It's a very often written about topic. I'm sure I don't need to tell people at I/O about all of the high-profile leaks that have happened or botnet attacks that have happened. But what is going to drive more security in IoT, I think, starts with identity and having a strong underlying identity for our products. So we want to make sure that whatever we choose is going to allow us to put a cryptographically strong and unique identity on the boards that we're going to use in the demo today. And next is scale. And I think there's a few things to think about when you are thinking about scale in the context of IoT. One is we are thinking about large numbers of devices. So over time, we think there might be millions or tens of millions of devices that we might sell into market and need to connect to this cloud. So we need a solution that we know can scale up to very large numbers of devices. But we should also realize that at the very beginning, your IoT deployment or solution might be just like ours is on stage, where you have just one or two devices. And for this reason, you want whatever you choose to scale from an economic perspective when you still have just a few devices in market. So to do this today, we're going to use Google Cloud IoT Core. IoT Core is Google Cloud's managed service for connecting IoT devices to the Google Cloud network. It provides two important things that we're going to show today. So first is device identity. It provides a mechanism for distributing key-based identities to devices. So every device will end up with its own unique private key, as well as the corresponding public key trusted in IoT Core. These keys can be used in a couple different ways to connect and authenticate to the system, and Jonathan is going to talk more about that later. The other thing it offers is a protocol bridge and support for common IoT protocols like MQTT and HTTP. But this protocol bridge is completely serverless and will scale with our application. So it's easy to connect just a few devices to it, and we'll only have to pay for the bandwidth used by those couple devices. But it will also easily scale up to hundreds of thousands or millions of devices deployed all over the globe without us having to change any code or deal with managing the back end. But connecting the devices to the cloud isn't the whole story. We need to actually communicate back to the devices or leverage the data that they're sending to us if we want to build an actually useful application. And luckily, Google Cloud can help with this too. So we're going to today try to leverage all serverless tools that will scale elastically with your application the same way that I just talked about IoT Core doing. So the first thing that we're going to use is Google Cloud PubSub. So all data sent from IoT devices into IoT Core end up as a message on a Cloud PubSub topic. PubSub, if you're not familiar with it, is a scalable message bus to build event-driven serverless or microservice applications. So you'll never have to worry about scaling for peaks or dealing with losing data. The next thing we're going to use is Cloud Functions. So a Cloud Function is a small snippet of code that can be written in a few different languages that are supported right now. And it allows you to do event-driven development. So this function can fire every time an event occurs or at a regular interval. In this case, we're going to use it to process each message and each event that comes into our PubSub stream. This will make it easy to, again, scale our application, but also build it. And finally, we're going to use Cloud Firestore. Firestore is a flexible NoSQL database hosted and managed by Google Cloud. And you'll see the query system and real-time update nature will make it easy for us to build this application, but also in the future build a mobile application or other application that leverages that data. Google Cloud has dozens of other services that can help with building your application, but these are the few that we're going to use for the demo today.
All right, so let's get to some of the fun stuff and actually show you how we can build some of it. Now, as mentioned, Thread support for IP makes it possible for a Thread device to communicate securely and end-to-end with IoT Core. In the middle, there is a Thread border router that's responsible for forwarding packets between the Thread network and the public internet. And note that the Thread border router simply forwards IP packets at the network layer and does not need to implement any application layer logic or proxy. In fact, the Thread border router has no knowledge of MQTT or HTTP, making it easy to deploy new applications without having to update or maintain application layer proxies in between. Now, 3 years ago, here at I/O, we launched the OpenThread project. OpenThread is an open source implementation of Thread, and it is the same implementation that's used in Nest products, including the Nest Hub Max that was announced here at I/O. The OpenThread project is hosted on GitHub and licensed under BSD3, and it's seen widespread adoption. OpenThread has been ported to more than 10 different 802.15.4 radios, and you can find example drivers for each of those in GitHub. Now, in today's demo, we'll use the Nordic NRF52840 system on chip. We actually brought a few of those here with us today for use in our demo, so let's take a look at them on stage. You'll see a couple dev boards on the right, and then a USB dongle attached to a Raspberry Pi on the left. The NRF52840 is built around a 32-bit ARM Cortex-M4 with 256K of RAM, 1 mega flash, and they're really intended for low-power, low-cost applications. And these dev boards are publicly available, which means you can go home and play with and replicate everything we've done on stage today. All right, so let's get back to the slides. All right, so let's get started with MQTT. Now, for those of you that don't know, MQTT stands for Message Queuing Telemetry Transport and is one of the most popular transport protocols used in IoT applications today. MQTT implements a publish-subscribe model on top of TCP/IP. Now, in this example, we'll walk through how to build an MQTT over Thread endpoint that communicates securely end-to-end with IoT Core. We will leverage third-party software. For networking, we'll use lightweight IP or LWIP, allowing us to leverage application frameworks that have already been built on top of LWIP, including MQTT. For security, this example leverages Mbed TLS and a JOT-C library for security. And for the RTOS, we'll use FreeRTOS. Now let's walk through some of the code. So here's the main control loop that runs on the Thread device. It's pretty simple. It starts by establishing an MQTT session to IoT Core, and then it sits in a while loop, publishing telemetry events every 2 seconds. So let's dive into the connect method first. The first step is to specify the MQTT connection parameters. MQTT uses TLS for transport layer security, so we have to set up the private key and certificates for use for TLS. We also need to specify other MQTT parameters, such as the client ID and keep alive values. Now, at the bottom, the device must also prepare a JSON Web Token. Let's take a closer look at what that JSON Web Token is. Now, as Calum mentioned, IoT Core provides a device identity system. A JSON Web Token, or JOT, is a compact, URL-safe means of representing claims and is used for device authentication with IoT Core. A JOT is composed of 3 sections: a header, a payload that contains a claim set, and a signature. The header and payload are JSON objects. And the header consists of 2 fields that indicate the signing algorithm and the type of the token. The example here uses RSA, but IoT Core also supports elliptic curve. Now, the payload contains a set of claims that is signed using asymmetric keys. IoT Core requires 3 claims: the issued at, which is the timestamp at when the token was created; the expiration, that is the timestamp when the token stops becoming valid; and audience, that contains the cloud project ID where the device is registered. And then finally, the signature contains a cryptographic signature of the concatenated header and payloads. So in code, creating a JOT looks like this. It leverages the JOT-C library, and we first create the object, then set the signing algorithm for the JOT. We add the issued at, expiration, and audience claims. And finally, we call JOT encode stir, which generates the signature and writes it out in the proper encoding. So that's how we generate a client's authentication material for IoT Core, and more generally, the MQTT connection parameters. The next step is to perform a DNS lookup for the MQTT endpoint, in this case, mqtt.googleapis.com. Now, with the IP address for the MQTT endpoint, we can then initiate an MQTT connection. So that was connect. Pretty simple. So now let's take a look at how to publish telemetry events using MQTT. In this example, the telemetry events are really simple temperature data. The first step is to format the payload, in this case using JSON. And then we call MQTT publish with the payload and specify an MQTT topic of /devices/MQTT-device/events. MQTT-device specifies the device ID, and events indicates that this is a telemetry event. That's it. Pretty simple. So now let's take a look at what how this works in a live demo. In this demo, we'll be using a Nordic dev board as the MQTT endpoint. The Nordic dev board communicates securely end-to-end with IoT Core's MQTT bridge. Now, the thread border router will use a Raspberry Pi with the Nordic USB dongle. And for the cloud application, we'll have a simple cloud function that processes telemetry events and saves them to a Firestore database. So let's take a quick look at the physical devices again. So the dev board in the middle will be the one that we use for the MQTT endpoint, and that'll communicate wirelessly via the Raspberry Pi end-to-end with IoT Core. So now let's switch over to my laptop and show you some live demos. So first thing I'll do is actually pull up on the cloud side, just kind of show you the cloud function here. So the cloud function listens for the topic temperature events, and each time that it's triggered, it simply decodes the payload, which includes the temperature data, and puts that into a Firestore database. It's a very simple cloud function. And then in our Firestore database here, we have a collection that's just for this demo. And then we have a document for the MQTT device itself. And of course, we have some data that's set to 0 for now. Now, if we go over here, I have a console open to a Raspberry Pi. So as you know, the Raspberry Pi is the thread border router. If I do an ifconfig, you'll see at the bottom the WPAN 0 interface is the network interface that represents the thread network. As you can see, the thread network itself appears as a standard Linux network interface, just like Wi-Fi or Ethernet. What I'm going to do next is start a TCP dump on the WPAN 0 interface so we can kind of see some traffic that's going over that thread network. Now, what I have also attached to my laptop is the MQTT endpoint. So I'll open a terminal there. And it has a very simple, remember this is an embedded device, so it doesn't even have a proper terminal, but it has a very simple CLI. And I do IP-adder to list its IP addresses. Of course, nothing's listed yet because it's not connected. So if I bring the interface up and start the thread service, and wait a moment, you'll see now that it has IP addresses because it's now connected to the thread network and has obtained the necessary information to configure those IP addresses. And finally, I'll start the MQTT service. Go back over to the TCP dump. The first thing you'll see is an NTP request response. That's the device itself synchronizing with global time. And then after some amount of time, you'll start to see TCP traffic. That TCP traffic is the MQTT session itself. Of course, we can't see the payload because it's within a TLS encrypted session. But this is to show you there's actual TCP traffic happening. You'll see messages pop up about every 2 seconds. And you'll see the actual data being presented here live. And every time it receives a new message, you'll see that field popping. So that's it. So that was our first demo, demonstrating MQTT talking end-to-end securely with IoT Core.
All right, awesome, Jonathan. Yeah. I believe that is the first time publicly that we've demoed any TCP protocol and MQTT over a thread network. So that's pretty exciting, going all the way to IoT Core and then up into our very simple database application. So that's really great, but MQTT and TCP still require a fair amount of power. This would maybe be good for a device which has mains power, is connected all the time, but that you still need low latency communication back down to, like a light switch or a light bulb. But now let's think about a much more constrained device. I talked about at the beginning wanting to be able to power a device on just a small coin cell battery. So let's talk about using COAP with IoT Core. So if you're not familiar with COAP, it's the Constrained Application Protocol. And it's a specialized web transfer protocol that's made for basically exactly what we want to do, very constrained devices and using very small amounts of power. COAP is designed to be a lot like HTTP, and it implements the widely used REST model. So servers make resources available under a URL, and clients access those resources using the familiar REST methods like get, put, post, delete. COAP was intentionally designed to resemble HTTP to make it easier for developers to build applications with it. But there are some differences. So at the network layer, you can see it's exactly the same, IPv4 or IPv6. And that's exactly what's going to make it easy to use with our thread network. But the primary difference is on the transport layer. With COAP, we'll be using UDP as opposed to TCP. And because of that, for transport layer security, we'll also need to use DTLS, or datagram transport layer security, which is specifically designed to function similar to TLS and provide similar levels of security for UDP connections. And finally, at the top, we'll use COAP. But from a developer standpoint, this should look mostly like accessing HTTP interfaces. Unfortunately, IoT Core does not natively support COAP. But because COAP and HTTP are so similar, it's very easy to build, implement, or use one that's already out there, stateless COAP to HTTP proxies. So in this case, what happens is we'll use the proxy URI option in COAP. An option in COAP is basically the same as a header in HTTP. And we will include information about the URI of the address that we would like to access. We would like the proxy to access for us. And what will happen then is the proxy will initiate and make the HTTP request, receive the response from the server, and then return the response as a COAP response, which is a little different than HTTP. But this allows the COAP endpoint to use a RESTful HTTP service pretty much as if it was accessing it directly, but still getting the benefits of low-power design and COAP. It's important to note that the COAP-HTTP proxy, Jonathan will talk more about code availability later, but the one that we'll use in this demo is available for you to go download and run. It's completely stateless, so it should scale very easily with any application using COAP and the IoT Core HTTP bridge. So without further ado, let's get into it and see it happen.
Yeah. So let's see how we can build a COAP endpoint that communicates with IoT Core. Now, as with the MQTT example, thread support for IP makes it possible to communicate securely end-to-end. But compared to the MQTT example, one difference is the introduction of the COAP proxy that Calum was talking about. Now, just to remind everyone, the proxy provides pass-through authentication passively to IoT Core, relaying device credentials directly to IoT Core, and the proxy doesn't do anything to validate it. The incoming COAP payload is converted to the required format for IoT Core HTTP bridge. And the responses from IoT Core's HTTP bridge will be returned to the client with an appropriate COAP response code. Now, here's the software architecture. You may note that this appears much simpler than our MQTT example. This example runs in bare metal environment and does not include an RTOS. This example also does not include a third-party IP stack and other application frameworks. The COAP protocol is actually used within Thread itself, so this example can actually leverage the same COAP implementation that's within OpenThread. So in short, what makes this example really attractive is the ability to operate in very constrained devices that have limited memory and code space. Again, the code has two high-level functions. The first is to establish a secure connection, and then followed by publishing telemetry events via that secure connection. So let's take a look at establishing that secure connection first. For simplicity, this example uses a hard-coded IP address, but we could have done that using a DNS lookup, as in the MQTT example. We also need to set up the security credentials for establishing the secure session. Here we use a pre-shared key cipher suite. Finally, we call OT COAP Secure Connect to establish the DTLS session. So let's take a look at the COAP-HTTP Proxy implementation in this demo. In this example, the COAP proxy listens on a specific path /GCP, and the proxy URI option includes the request URI path that the COAP proxy uses when translating that request on behalf of the COAP endpoint. And it includes things like the project ID, device ID, and the publish event action. So with COAP, we use the post method to publish telemetry events. The first part of generating the COAP post request is to set up the COAP header. This includes specifying the path, GCP, and the COAP proxy URI option along with the publish event subpath that indicates that this is a telemetry event. So let's dive into that proxy URI option a little more. First, we format the proxy URI path that the COAP proxy uses when translating this request, again, including things like the project ID, registry ID, device ID. And then we include the JOT, which includes the claims that specify the issued at, expiration, and audience claims that we talked about earlier. We then pass that proxy URI string to JOT create for encoding and signature generation. And once we have the JOT, we add that to the COAP header in the proxy URI option. So that was generating the COAP header with the proxy URI option. Now let's take a look at the COAP payload itself. Again, it's pretty simple. Here we format the telemetry event data in JSON format, as we did in the MQTT example, and then we append that to the payload of the COAP message. Pretty simple. So now with the complete COAP request message, we can send that request to the COAP proxy. So now let's take a look at, again, how this looks in action. Again, we'll use a Nordic dev board that operates at this COAP endpoint. And that Nordic dev board communicates wirelessly, again, via the Raspberry Pi, serving as the thread border router. Difference here is that rather than communicating directly to IoT Core, it is communicating with the COAP proxy. The COAP proxy then statelessly translates that message into something that IoT Core can understand, which is HTTP. Now, on the cloud side, again, we use the same exact cloud function and Firestore database as we did with the MQTT demo. So let's go back to my laptop. So here, it's the same screen that I left it. You can still see the MQTT device still publishing data every 2 seconds. But I have another document here, which is for the COAP device itself. And of course, because I haven't turned it on, the data is still set to 0. Now, if I move back to the console real quick, again, TCP traffic flowing through the thread border router on the thread interface. And on the desk here, if I pick it up, here's the COAP endpoint. It's a Nordic dev board. And the difference here, rather than being plugged in, just to show how low power is, this dev board actually is powered off a coin cell battery. Right. So all I'm going to do is turn the dev board on. You'll see some green LEDs, hopefully, blinking. And what you start to see here is, again, an NTP message for this device to get global time. You start to see some UDP traffic up in the console. That was the DTLS session itself being established. And in this case, it is event triggered. So if I push a button here, you'll see UDP messages. And those UDP messages actually are the COAP messages being transmitted by this device through the thread border router. And if I switch back to the Firestore database, the COAP device information, you can see now that that counter value is being updated each time I press the button. Pretty cool. So that was the COAP demo.
Now what we've shown is 2 thread devices talking through the same border router using standard IP technology. In this case, we are talking to the same service and the same ultimate database. But the important thing to note here is we could just as easily have been talking to 2 completely different backends. These could be 2 devices from 2 different vendors. But they're interoperating at the network level and going through the same border router without having to worry about or have any knowledge of each other. So I think that pretty much wraps it up. Hopefully, this shows how you, as developers, can think about and use Thread. And as border routers become more prevalent, you can worry about just building your devices and having them talk to your backend services wherever they might be hosted using standard IP technologies. So if you want to see the tutorials and code, we have it posted for both the demos at these links. And if you have questions, Jonathan and I will be right outside afterwards. So thanks very much.
Thank you.